We'll try to make it interesting for you. Okay. So pretty quickly, my name is Shai. I'm from ScaleMP. We provide virtualization solution for high-end computing. Our virtualization solution, you can see it here, takes multiple independent servers, virtualize them as one, so we can take a herd of penguins and make one big fat penguin running on multiple operating systems. If you haven't heard about ScaleMP yet, we Israeli-based startup, started in 2003. We can create virtual machines that goes all the way to 128 systems, which is 16,000 cores and 64 terabytes of memory. It's processor and interconnect agnostics. Most of our business, or all of our business today, in x86 space and InfiniBand. And we have about 300 customers. We have like 2 or 3 customers here in Israel. What customers do with that? So we can look here on a list of applications, and we can identify applications in different verticals. Some of them are MPI applications. Some of them are OpenMP applications, multi-threaded. Some of them are pthreads. Some of them are single-threaded applications that require lots of memory. And we see that they are across the boards in different verticals. So virtualization for high-performance computing is used across many verticals. And if we look on the customer names, everyone here needs to be, if you can't identify 2 logos, then you have a problem. You can at least identify that one here and choose another one. Okay. So just to put things in perspective, virtualization is an abused term. And on the left-hand side of this slide, on the right-hand side of this slide is kind of opposite from here. That's interesting. So on the when you're looking at it on the left-hand side of this slide, we can see the VMware style virtualization when we take a single server and create multiple isolated virtual machine. Each one of them can run independent operating system. There are multiple solutions in this market. You can see a list of companies here at the bottom. What we bring to market is the ability to take multiple servers and create a virtual machine. Now, these 2 virtual machines are different. And I'll give you just one difference between them. The virtual machines here, if you aggregate the resources, the virtual resources will be bigger or greater than the physical resources. So let me explain that. Let's say that we have here 3 virtual machines, and we count the number of virtual CPUs we have, or we count the amount of memory we have. That will be more than the physical resources we have in the server. So the first company to identify that was VMware. Is there anyone here heard about the recent, not so recent, about 6 months ago, change in VMware licensing model? Okay, Rich. You're not the typical audience. So VMware originally was pricing their product as a license per server. Okay, so you buy a server, you put the VMware license on top of that, then you start lots of VMs. Now VMware has lots of programmers, and they're buying like half the valley around the Stanford. It's very nice. You can see how they take space of other companies. And all these programmers are sitting there, and they are optimizing their hypervisor. So they're optimizing the hypervisor, and now you can take a server, and instead of being able to run their 10 virtual machines, you can run 20. So guess what? Now the customer can run VMware on 1 server instead of 2. So VMware is losing money by doing that, right? So VMware changed their licensing model, and they count how many, not how many VMs you have, what's the aggregate resources you have in the virtual machine. So if you have 10 virtual machines, and each one of them has a 64 gigabyte of virtual memory, then you need to pay them for 640 gigabyte of virtual memory. So you price it by the virtual resources. The virtual machine on the right has the same or lower virtual resources compared to the physical resources. So if you have 4 servers there, and each one of them has 2 sockets and 64 gigabytes of memory, the virtual machine there will show you 8 sockets, not more than 8 sockets, and it will show you 256 gigabytes of memory, okay, not more than that. So the virtual to physical resources on the right-hand side there, you will have the virtual resources will be same or lower than the physical, and on the left-hand side, what you'll see the virtual resources will be more equal or more than the physical resources. Very important to understand that. So why is that important? With this type of technology, you can save OPEX, and we'll talk why it saves OPEX, and it saves CAPEX. It saves you money to buy big systems, and we'll talk about that as well. And it gives you more flexibility for the infrastructure on one end, and on the other end, more performance. So let's talk how we do all this magic. So we spoke about virtual SMP. I showed you before how that thing works. And we have 4 use cases. First, applications that require large memory. So for applications like that, we can run our application on a single server. So that's our server. Server is I/O, CPU, and memory. But the problem we have is that we are bounded by the memory size. We want to have more memory. So in this case, we'll take multiple additional systems. We'll put our virtual machine on top of that, our hypervisor on top of that. The hypervisor will show us a virtual memory, okay? That for the operating system will look like a physical memory. That is the aggregate amount of memory of all the systems. Our software will take care of memory coherency and moving the memory around between the boards, making sure that the application gets great performance. In that case, you get the memory of all the nodes and the compute and I/O of the one node you had to start with. Second case will be an application that is fine with the memory and fine with the compute it has, but it's kind of under pressure on the I/O side. Let's say that you need to put lots of network controller or lots of storage controller, and you just can't fit them into a server. An example for that will be scratch space. You need to have very, very fast scratch, but in your server there are only 2 drives. What you do now? Okay, you can buy another server, you replace the server with a bigger server, maybe then put the SSD storage, and so on. That's one option. The other option is take yourself, let's say, 10 servers and aggregate all the drives together. Now you have 20 drives. Okay, so your random access performance is much faster. A third case will be application that is multi-threaded. Multi-threaded, and you can add more threads, but you are limited by the number of CPUs you have in a box. So in this case, we will aggregate the CPUs of multiple systems, and your application will use the memory, the I/O, which it was fine with to start with, but the CPUs of all the rest. Now, all these 3 cases are very synthetic. In real life are more complicated than any other slide. In real life, what happens is a real-life application will be a combination of those. It will be bounded by memory in some cases, it will be bounded with CPUs, be bounded by I/O, and through the life cycle of an application, what we can find out is that sometimes we are limited by one, limited by others, or limited by some kind of combination of them. Now there is a 4th case. The 4th case is not relates to application that is limited by its by the system side, but it's limited by the way we manage applications. We spoke a lot about clusters today. So here is my cluster. I have 4 servers, and I'm running my API application. And the problem I have with that is that it's difficult to manage it. I have 4 machines. I need to manage distributed storage. I need to, we heard here about lots of optimization I need to do with InfiniBand in order to have that working at best performance. And here virtualization can play a big role in simplifying clusters. So here's my cluster. I'm putting my virtualization engine on top of that. It's becoming one machine, one operating system, and I'm going and running my MPI or throughput application on top of that. I'm managing one machine from management perspective, but in reality I have multiple physical boxes underneath. So these are the 4 usage models. Now, if what I'm saying makes sense, I need to show you a proof point that case A, B, and C, we can show some decent performance. Because if we cannot show decent performance, then we have a problem. So that's number 1. Number 2, what we need to show here is that if we'll take a cluster and run our application on a cluster, and then we put VSMP on top of that, we'll make that a virtual shared memory system and run the same cluster application, the same MPI application on top of that. Now we made our life much easier because we have just one environment to manage. We would really like the application to run the same performance. Okay, so I'm going to show you performance of these 3 cases. I don't think I prepared slide for here, but you can look. There is quite a bit of public data comparing MPI application running on native cluster and running on virtualized environment by ScaleMP, and it's basically the same performance. So the first, one of the cases where there were CPUs, so here's an example of comparing a OpenMP application written with Fortran, running on a physical shared memory system here by SGI. Is there anyone didn't heard about a company named SGI before? Okay, there are 2. Okay, 3, 4. Okay. So SGI build large-scale x86 systems, and here a customer measuring the performance of their machine, and you can see the performance on 32 core, 64 core, 96, 128. Very, very nice. And then it's running on a VSMP foundation, a virtualized environment, about basically apples to apples, and we can see that the performance lower is better here. Not talking about price, of course, there is like, our solution is less than half the cost, but what's interesting here is give you 10 to 15% better performance. That's interesting. Second case here is we're looking to memory bandwidth, and in this case here, we spoke about memory. One of the cases was memory. We are using a StreamOMP memory bandwidth test to test the performance of virtualized system. So let me just walk you through this slide. 1 core Nehalem Westmere EP give you about 9 gigabytes per second. A full socket, 6 cores, give you 23 gigabytes per second, so 6 times the compute, 2.5 times the memory bandwidth. That means 42% efficiency. Second socket, you go to 40, not exactly linear. Linear is 23 to 46. You go 23 to 40, not exactly linear. Efficiency drops to 36, and that's the end of the box. Now you put VSMP foundation on top of that and add enough boxes, and let's continue run our benchmark. On 24, we go to 40 to 80, that's linear. 48, we go to 159, almost linear. And if we look on that here on this chart, which is give us the efficiency based on the 12 core performance, we see that we go from 12 cores to 768, so 64 times, 64x number of units, and we get 87% efficiency. Just to remind you, on an Intel CPU from core 1 to core 2, you get 76% efficiency. So go figure, which give you better performance. Last but not the least, I/O performance. In many cases, customers looking to run a fast Scratch. Scratch is very, very important in order to increase the overall performance of HPC applications. In this case, what we are comparing is the performance of a device from a company named Fusion.io. Anyone here heard about the company named Fusion.io in the past? Okay, you know what Fusion.io is doing. So Fusion.io give you a PCI Express a flash that give you high IOPS and high bandwidth. This is comparing the bandwidth, of course. So Fusion.io will give us a constant rate of 6 gigabytes per second for read and 4.4 gigabytes per second for write. What we are doing, we take 8 pizza boxes, each one 2U pizza boxes. You know, think about it like a $4,000 pizza box, $4,000 in States. In Israel, everything costs a little bit more. In each pizza box, we have 8 drives and a HBA, a SAS HBA. We connect them and we run a test. Our test runs on the CPU, the first CPU of the first box. So we don't use any of the additional compute coming from the additional boxes. Again, we're looking into serial workload, and our serial workload can generate here on the first node about 1 gigabyte per second. That's what we can suck out of the drive, and we start adding nodes. And we go from 1 node to 8 nodes. Now we use all the drives in all the nodes. Again, the operating system will see all the I/O subsystem. So the operating system will see 64 drives, 8 drives for each one of the 8 nodes. And the operating system can make from all of that a single volume. And the performance we get is 7.5 gigabytes per second, almost linear. If you think about it, you go from 1 to 7.5, almost linear. And that's 20% better than Fusion.io. If you want to talk about cost, about 40% the cost. Okay?
This is all in InfiniBand bandwidth.
That's dual InfiniBand. Very important. And if you think about it, dual InfiniBand, we get here to a very high efficiency. This is specifically measured on FDR. Okay? And the guys here from Mellanox can give you all the details. So that's about that. You can see lots of performance data on our website. If you really have the time, there are like 60 different benchmarks there. Go and look at that. Skip that, and I'll show you a demo. Can you see any of that, or that's kind of...
Hardly.
Yeah, hardly. Okay, I'll jump into here. What I want to show you is how it looks when it boots. So think you have your cluster, you take multiple systems, you configure them to boot our software from the network, or you can have the software on a USB stick, you plug it to multiple systems. They boot, they create a virtual machine. On the virtual machine you load Linux, and here in Linux we look, and what we're seeing here, this is we're running here a command. Our user is root, our host is localhost. We run this command VSMP version, and we see that we are running on a machine with 64 nodes. That's the InfiniBand topology here. 128 sockets, Westmere EP, 6 terabytes of memory, blah blah blah. Booted the operating system from PXE. So what we do with that, we go on the operating system, same machine, you see the famous root at localhost, and we can see that we have 5.3 terabytes of memory to use. The rest of the memory is used either by our software or as a cache. And here is our first CPU in the system, processor 0, and Intel processors, as we said before, 5650. But if we'll do cat proc CPU info and we just grep that first line processor, we'll see all the 768 cores we have at the system. That's pretty nice. And last but not the least, we of course see all the I/O devices. And as you can see here, if you can barely see here, LSPCI output showing lots of NICs, the 2 NICs per server. Okay. Okay, so what we do with that? So we spoke about technology. We have technology that takes multiple systems, makes them one. We take lots of small penguins and we make one big penguin. And now we can do with that 3 things. We can use that to simplify a small cluster. So we have our small cluster, and we don't always know how to manage it because managing clusters is difficult. So we virtualize that to one system, and now we run it as one system. So that's our first case. Our second case, we can't use a cluster. We have to buy a big machine, and we need a big machine with lots of memory or lots of cores, and it's pretty damn expensive. And in fact, it's not just it's expensive, it's using like yesterday's technology. Because, for example, if you use our technology, you can create yourself a large machine based on Sandy Bridge these days. And if you buy a big machine, it will be like, if it will be x86, it will be Westmere. If it will be non-x86, maybe Power or Itanium or something like that you could put in the museum. You could buy it and put it immediately in the museum. You don't need to wait. With our technology, again, you can use the latest and greatest technology and save quite a bit of money there. And last but not the least is what we are calling cloud or on demand. We have that use case where customers are buying hundreds or maybe thousands of servers for a private cloud. In that private cloud, one of the problems you have is you really want to reduce the cost of the hardware. You want to have single, one type of server multiplied by a lot. And that allows you to keep maintenance costs down and use that for any kind of workload. The problem is that some of the workloads won't fit the box. So either you buy the largest box you can, that's expensive, or if you buy small boxes, what will you do with workloads that won't fit in the box? So the on-demand on-demand case allows you to provision VMs on demand when workloads need them. So think what you have this large cloud, and when you want, you can create VMs, and I'll show you that kind of in graphical manner. Since we're kind of short in time, I'll show you a couple of things that are not HPC specific. Talk about it. Yeah.
You must run applications that are really, really NUMA aware, because if you not be NUMA aware, then it can be disaster.
So we spoke about 3 different cases. Okay, so let's go over that again. Here you run a cluster. Okay, so clusters doesn't know anything about NUMA and doesn't need to know anything about NUMA. What you bring to the cluster case is instead of running multiple independent servers that communicate over TCP/IP or InfiniBand, okay, you make that one system and they are communicating shared memory. Who cares, right? No performance issue. In second case, when you look in these cases, again, I go back because maybe that lost in translation. We have three use cases when we talk about performance. We talk about large memory applications that do not need lots of CPUs, they need lots of performance. You don't need to be NUMA, you need lots of memory. You do not need to be NUMA aware. And I can tell you that the most demand today for our solution in that domain is for that. When you are buying informatics, your application is single-threaded, single process, single everything. You just need single big 8, 16 terabytes of memory. So you don't need to be any NUMA aware. You just need to give the application in a transparent way the ability to go into 4, 8, 10, 20 terabytes of memory because the application itself is single-threaded first. Second, when we talk about I/O, same story. Okay, the applications themselves running on few cores. Okay, usually the number of cores that you have in a pizza box, but it needs an I/O subsystem that cannot fit into a pizza box. And the last case, indeed, is applications that require quite a bit of CPUs, scalable applications. Since today, in most pizza boxes, you have 8 and very, very soon 16 cores, or if you use AMD platforms, in a pizza box you have 64 cores. It's very rare to find a shared memory application that scales to 64 cores, that you're looking to scale it further. So you pick up the phone and calling us, that your application is not NUMA aware to start with. Because if your application is not NUMA aware to start with, it's not going to scale to on a 64-core AMD platform. It's not, okay? It's going to scale maybe to 4 cores, 8, 16, maybe 32. But if when you run out of the box, then you call us. If your application can run on 8 cores, don't call us in order to buy 2 machines with 4 cores, okay? Buy the machine that you can buy like that and call us when that ends. If you get to that point, your application is a scalable application, and then everything else is a philosophical argument, and therefore it's irrelevant.
I have 2 questions. What if one of the box fails?
If one of the box fails, then what will happen is that the operating system will have to restart. Very similar to a cluster. If you have a cluster application, and you're running, again, I'm looking on this use case, you're running a distributed application, and one of the nodes fails, your job died. That's it. It's very rare to see applications that can handle a node failure in a distributed environment. There are cases like that, but usually you use checkpoint and restart for the application itself. But if you use checkpoint restart, you can use checkpoint restart on VSMP. Same.
Most distributed systems built for fault tolerance. We're not talking about MPI jobs and stuff like that.
So most distributed distributed environment built for fault tolerance, and even VSMP is built for fault tolerance. If you lost a node, the VM will come up without that node. That's granted. The question is, what's happened to your job? Your job died, it must be restarted, just like a cluster. Similar. Now, if you look into the large memory case, okay, for example, your application is not something that you would run on a cluster, then you have 2 cases. Either you just run it on a pizza box and a disk, and then go figure out what will happen when the disk will run out, or you're going to buy a big system, right? If you buy a big system, then you ask yourself the same question. What will happen if I'm buying my $1 million big system, and then I'm running out of 2 DIMMs that dies? You're basically in the same, call it the availability criteria. VSMP brings a couple of availability advantages by the fact that it's self-healing. If you lost a node, the VM will come up without that node. You can have redundant InfiniBand. You can have multiple InfiniBand backplanes. And if one of them will die, we'll switch to the other one without having the VM stop operating. That's kind of add-on features that you have compared to the typical application. I'll just mention one case, very, very unique case. If you're running an MPI application, if you're running a long jobs in MPI applications, one of the issues that can happen once in a while is that you lose a cable on your InfiniBand fabric. And if you have these issues on the fabric, then your job will die. It's very rare to find MPI libraries or MPI applications that know how to switch a cable, okay, when they're running. It's very rare to a level that it doesn't exist. With VSMP Foundation, transparent. You're running your MPI application, it's running in shmem, okay? You run 2 cables between all the nodes to the switch. You can even have 2 switches if you really want to invest money. And then take your application job, MPI job. Let's say that you have a job that can run for 3 weeks, and just to show the trust you have in our technology, wait for the third week just before the job ends and plug out one of the cables. I can guarantee you now that it will continue to work. So that's an advantage that you get over just the typical clusters. But let's run here. I want to show you something from the enterprise space. A cool example of what you can do with virtualization. So let's say that we are speaking here about cluster management, okay, this first case, and we all run, we already know this scenario, right, that we are going to have multiple nodes. Hi, I'm shy. I got you. So we have these multiple nodes, and we created our VM. Now let's have a look here what's happened to our VM. So we take our VM and we make a bigger one. So that's our big VM, and it's going to run an operating system. And guess what? It's going to run in a hypervisor. You can run in a hypervisor on top of our VM. So think about, take 4 nodes, put VSMP. On top of that, you put Red Hat, and Red Hat has a built-in hypervisor, right? And then you run multiple VMs. So yeah, you may ask yourself, why does that matter, right? I could have run Red Hat here on each one of these VMs and run these VMs here. But if you do that, you'll have to go and do load balancing and move VMs between the nodes here in the case that one of the VMs need more resources than others. So by the ability to create a larger flat resource, okay, that later on can be segmented, you get a much easier, again, ease of use for your cluster.
What happens when hardware fails here?
Same as I mentioned before.
Everything goes down.
Yep. Okay. So if you have a mission critical environment, if you do have something like that, just have another one next to it. And if you're in the financial space, and we have quite a bit of customers like that, just put it on the other side of the Hudson if possible. Okay, don't put it one next to each other. So what the game here is, again, cluster management. Just like in HPC, if we run a throughput environment, and we have our 4 servers, and each one of them will run 10 jobs, and we need to go and manage the resource, make sure that we have enough resources on each one of the nodes. Virtual machine run all the jobs on top, and VMs is just one additional type of job. Next, big machines. I think we discussed that and skipped that. I want to show you something about cloud. Okay, so we spoke. Yep.
Just one question about the disk. You create also a unique file system. I mean, with all the disk in each machine, in each box. How it works?
Okay, so what's happened is that we virtualize all the resources to the operating system. So when the operating system will boot up, if you have 10 machines and 2 drives each, the operating system is going to see 20 drives, the 20 physical drives you have. Now at the operating system, you can use a volume manager, okay, to take the 20 drives and make them single volume. The recommendation is for Scratch, if you're looking for Scratch performance, then use the MDADM, okay, to create a RAID 0 with the right block size, and go for it. Now everything that you write to the storage will be written to all the spindles in parallel, and you get the performance. Okay. And if you're looking for reliability, then you can use other strategies. But that's basically the idea. We don't virtualize I/O. We pass through it, flow it back all the way to the operating system. And same is true for networking. If you have 10 systems, you have 2 NICs on every pizza box these days, right? On the operating system, you'll see 20 NICs. You'll have ETH0 to ETH19. You don't have to configure all of them. You can go in and out from one NIC. But if your application is a bandwidth-sensitive application, for example, then you can bring all of them on, or maybe you can bond them at the operating system level.
You can bond them.
It's not we. You can bond. If you know how to use Linux, go and bond. We can give you the instructions if you want, but you can find that in any Red Hat system administration book. So a couple of interesting things about that one. So in the legacy environment, we will buy a cluster, right? And next to that, a big machine. In the next generation cloud or large-scale grid, we'll have our cluster here connected to, of course, Mellanox InfiniBand and all of that. And when we need our large-scale system, we virtually create one here, and one here, and one here on an on-demand basis. It can come from the job scheduler if you know how to do that, and there are several implementations for that. If you want to think about kind of visionary things, and that will be my last slide for the day, is think about that. We spoke about Amazon AWS a second ago.
One machine goes down, everything goes down.
Yeah.
You like that?
I know.
This is your motto.
Okay. One machine goes down, everything goes down. Sure.
Oh.
In this case here, we have our a private cloud, and each one of the nodes running multiple VMs, and we have excess resources. So we have spare resources on each one of the nodes. We can create ourselves a VM on each one of the nodes. That VM will suck out the spare resources for each one of the nodes, and then we aggregate these VMs and create for ourselves a VM that uses the excess resources from all the nodes. Yes?
Do you have this also for Microsoft Windows or just for Linux?
We are a virtual machine company. Operating system, you can run whatever operating system you want with a comment. Don't try to run Windows on a large virtual machine. You know, there is some limitation. The operating system was designed to run on a PC with a single core, so it's not really scaling. Our experience with trying to run Windows on 1,000 core machines or machines with 10 terabytes is just complete disaster. The only recommendation I can give you here is if you want to run Windows, then use this model I showed a second ago. This. Okay? Run yourself a good Linux that know how to take all the resources with KVM and put your Windows 2000 something within a VM that you can then play with its size. You'll get to a point that you'll see that Windows, that's it. Anything else? Thank you very much, everyone.